Dear students, today we shall discuss how to find an intrinsic equation of a curve. Let's take one more example for finding an intrinsic equation when the curve is given in the Cartesian form. Show that the intrinsic equation of the semi-cubical parabola 3a y square is equal to 2x cube is 9s is equal to 4a into sec square psi minus 1. It is sec cube psi minus 1. Now since equation of the curve is 3a y square is equal to 2x cube, so we differentiate it, so we get 6ay dy by dx is equal to 6x square. So therefore dy upon dx is x square upon ay. Substitute the value of y from here. So this is x square upon a into 2x cube upon 3a raised to the power half, which is under root of 3x upon 2a. Now we know that dy upon dx is tan psi. So therefore tan psi is equal to under root of 3x upon 2a. Now s is given by 0 to x under root of 1 plus dy by dx whole square dx. Because 0, 0 is a point of this semi-cubical parabola and xy is the variable point, so x coordinate is x. So this is equal to 0 to x under root of 1 plus, now dy upon dx whole square is 3x upon 2a dx, which can be written as 0 to x 1 plus 3 upon 2a into x raised to the power half dx. So integrating it, we get 1 plus 3 upon 2a into x raised to the power 3 by 2 divided by 3 upon 2 into 3 upon 2a, limit 0 to x, which comes out to be 4a upon 9, 1 plus 3x upon 2a raised to the power 3 by 2 minus 1. Now in place of 3x upon 2a, we put tan square psi. So therefore s is equal to 4a upon 9, 1 plus tan square psi raised to the power 3 by 2 minus 1. Now 1 plus tan square psi is sec square psi raised to the power 3 by 2 is sec cube psi minus 1. So therefore cross multiplying, we get 9s is equal to 4a into sec cube psi minus 1. Now let's discuss how to find an intrinsic equation when the curve is given in the polar form. So suppose that equation of the curve is r is equal to f theta. Now look at this diagram. This is the curve r is equal to f theta. Now we take any point P having polar coordinates as r comma theta. So therefore this length is r and this vectorial angle is theta. Now we draw a tangent at P, right? And suppose that angle between this radius vector and this tangent is phi. Then as you know that exterior angle is sum of the opposite interior angles. Now because this is phi, so this is also phi. Now we know that from differential calculus that tan phi is equal to r into d theta upon dr, that is r upon d theta. Now r is f theta, dr upon d theta is f dash theta. Psi is equal to theta plus phi. Suppose that alpha is the vectorial angle of this point A, then s is given by alpha to theta under root of r square plus dr upon d theta whole square d theta. Now r square is f theta whole square, dr upon d theta whole square is f dash theta whole square, then d theta. Now eliminating theta and phi from equations 1, 2 and 3, we'll get the relation between s and psi, which is the required intrinsic equation of the given curve. For finding out intrinsic equation when the curve is given the parametric form, we make use of the same method which we adopted while finding out intrinsic equation when the curve is given in Cartesian form. We'll take few examples. And the last one is intrinsic equation from the pedal equation. Suppose that pedal equation of the given curve is p is equal to f of r. Then from differential calculus we know that s is given by a to r, r upon under root of r square minus p square ds, where the arc length s is measured from the point for which r is equal to a. Radius of curvature is given by rho is equal to r dr upon dp. Now rho is given by ds upon d psi. So then eliminating P and R from equation number 1, 2 and 3, we will obtain relation between S and psi, and therefore we get the intrinsic equation of the curve. Now let's take few examples. Show that the intrinsic equation of the cycloid x is equal to a into t plus sin t, y is equal to a into 1 minus cos t, is S is equal to 4a into sin psi. Hence or otherwise find the length of the cycloid. Now here curve is given in the parametric form. So to find dy upon dx, we shall make use of the formula dy upon dx is equal to dy upon dt divided by dx upon dt. Now from the curve, equation of the curve, we have dx upon dt is equal to a into 1 plus cos t, and dy upon dt is equal to a into sin t. So therefore dy upon dx is dy upon dt divided by dx upon dt, that is a sin t divided by a into 1 plus cos t. Sin t is 2 sin t by 2 cos t by 2, 1 plus cos t is 2 cos square t by 2. So therefore this comes out to be tan t by 2. So therefore tan of psi, because dy upon dx is tan psi, so tan psi is tan t by 2, that means psi is equal to t by 2. We shall make use of this relation later on. If S denotes the arc length of the cycloid measured from the vertex, that is at the point where t is 0, to any point P, that is the point T, in the direction of t increasing, then we know this formula S is equal to 0 to t under root of dx upon dt whole square plus dy upon dt whole square dt, because at the vertex t is 0. So this is 0 to t under root of dx upon dt whole square is a square into 1 plus cos t whole square, dy upon dt whole square is a square sin square t. 1 plus cos t whole square can be written as 1 plus 2 cos t plus cos square t, and then this sin square t. Take a square outside, so this is a times 0 to t under root of, now cos square t plus sin square t is 1, so we take 2 common, so 2 into 1 plus cos t dt. 1 plus cos t is 2 cos square t by 2, so this is a into 0 to t under root of 4 cos square t by 2 dt. So this is 2a times 0 to t cos t by 2 dt. Now integration of cos t by 2 is 2 sin t by 2. Put the limits, so this is 4a sin t by 2. Now as we obtained psi is equal to t by 2, so put t by 2 is equal to psi, therefore S is equal to 4a into sin psi. So this is the relation between S and psi for the given curve. So therefore this is an intrinsic equation of the given cycloid. Now in the next part we have to find out length of the cycloid. Now you remember that we have taken the formula for S, and in S we take t from 0 to t. Now at this point we have t is equal to 0, and here at the cusp we have t is equal to pi. Now because psi is t by 2, so therefore at this point psi is 0, and at this point psi is t by 2. So we will find out length of this portion and then multiply it by 2. So if S1 denotes the length of the arc extending from the vertex to a cusp, then S1 is equal to 4 into sine pi by 2, that is 4a. So therefore whole length of the cycloid is 2 into 4a, that is 8a. Next example, when the curve is given in polar form. Find the intrinsic equation of the cardoid r is equal to a into 1 plus cos theta. Let's do this part, then we will do second part. Now r is equal to a into 1 plus cos theta. So therefore dr upon d theta is minus a sin theta. Tan phi is given by r into d theta upon dr, that is r divided by dr upon d theta. Put the values, r is a into 1 plus cos theta, dr upon d theta is minus a sin theta. 1 plus cos theta is 2 cos square theta by 2, sin theta is 2 sin theta by 2 cos theta by 2. So therefore tan phi is equal to minus cot 3 by theta by 2. which can be written as tan of pi by 2 plus theta by 2. So therefore phi is equal to pi by 2 plus theta by 2. Now we make use of this relation, psi is equal to theta plus phi. Put the value of phi from here, so we have psi is equal to theta plus pi by 2 plus theta by 2, that is psi is pi by 2 plus 3 upon 2 theta. So therefore psi minus pi by 2 is 3 upon 2 theta. So therefore theta by 2 is 1 upon 3 psi minus pi by 2. We shall make use of this relation later on. Now if S denotes the arc length of the cardoid measured from the vertex, that is theta is equal to 0, to any point P corresponding to theta in the direction of theta increasing, then S is given by integral 0 to theta under root of r square plus dr upon d theta whole square d theta. Substitute the values of r and dr upon d theta. So S is equal to 0 to theta under root of a square into 1 plus cos theta whole square plus a square sin square theta d theta. Simplify it, we get S is equal to 2a times 0 to theta cos theta by 2 d theta. Integrating, we have 2a times 2 sin theta by 2 0 to theta. So therefore S is equal to 4a sin theta by 2. Put the value of theta by 2 from here. So S is equal to 4a sin 1 by 3 psi minus pi by 2. This is the first one, because we get the relation between S and psi. So this is the intrinsic equation of the given curve. Now in the second part we have to prove that S square plus 9 into rho square is equal to 16a square. Rho is the radius of curvature. Now we know that rho is equal to ds upon d psi. So differentiate this with respect to psi. We have rho is equal to 4a into 1 by 3 cos 1 upon 3 psi minus pi by 2. Cross multiplying by 3, we have 3 rho is equal to 4a cos 1 by 3 psi minus pi by 2. Now to prove the required result, we square and add these two equations. So S square plus 9 rho square is equal to 16a square, and then you know that sin square theta plus cos square theta is 1. So therefore S square plus 9 rho square is equal to 16a square. Let's take fourth example. Find the intrinsic equation of the equiangular spiral P is equal to r sin alpha. This is the pedal equation. So P is equal to r sin alpha, that means dP upon dr is sin alpha. So therefore radius of curvature is given by r into dr upon dP, that is r divided by dP upon dr, that is r upon sin alpha. So therefore rho is equal to r into cosec alpha, and we know that rho is given by ds upon d psi, so therefore ds upon d psi is r into cosec alpha. This is equation number 1. Now if the arc length is measured from the point r is equal to 0 in the direction of r increasing, then S is given by integral 0 to r upon under root of r square minus p square dr. So this is 0 to r upon under root of r square minus, now p square is r square sin square alpha dr. So therefore S is equal to 0 to r upon r cos alpha dr, which is 0 to r sec alpha dr, sec alpha into r, which is r sec alpha. So therefore S is equal to r sec alpha. Now divide 1 by 2, we have ds upon d psi upon S is equal to cosec alpha upon sec alpha, which is 1 upon sin alpha divided by 1 upon cos alpha, that is cot alpha. So therefore from this equation we have ds upon S is equal to cot alpha into d psi. Now integrating, we get log S is equal to psi cot alpha plus log of c. Take log c on the left hand side, so we get log of S upon c is equal to psi cot alpha. So therefore S upon c is equal to e to the power psi cot alpha. So therefore S is equal to c into e to the power psi cot alpha. So this is the required intrinsic equation of the given curve. Now let's take the last example. Find the intrinsic equation of the cardoid r is equal to a into 1 minus cos theta. Now r is equal to a into 1 minus cos theta, so therefore dr upon d theta is a sin theta. Now tan phi is r d theta upon dr, which is r upon dr upon d theta. Substitute the value, so we have a into 1 minus cos theta upon a sin theta. 1 minus cos theta is 2 sin square theta by 2, sin theta 2 sin theta by 2 cos theta by 2. So therefore tan phi is equal to tan of theta by 2. That means phi is equal to theta by 2. Now make use of this relation, psi is equal to theta plus phi. So therefore psi is equal to theta plus theta by 2, which is 3 upon 2 theta. Now again s is given by 0 to theta under root of r square plus dr upon d theta whole square d theta. Put the values of r and dr upon d theta. So we get s is equal to 2a times 0 to theta sin theta by 2 d theta. Integrated, we get 4a times minus cos theta by 2 0 to theta, which is 4a times 1 minus cos theta by 2. Now 1 minus cos theta is 2 sin square theta by 2, so therefore this is 2 sin square theta by 4. So this is s is equal to 8a into sin square theta by 4. Put the value of theta from here, 2 upon 3 psi, so therefore s is 8a sin square 1 by 4 into 2 by 3 psi. So therefore s is equal to 8a sin square psi by 6. So this is the relation between s and psi, which is the required intrinsic equation for the cardoid r is equal to a into 1 minus cos theta. Thank you so much.